So, good morning all. I welcome you all to this 5 days Gyan course on biofluid mechanics, mathematical modeling and challenges. So this short course will explore some of the important research issues and challenges in using computational simulations to study fluid flow, mass transfer and chemical reactions in biological systems. We will look at applications in areas such as the cardiovascular system, blood clot formation and breakdown, and drug transport inside solid tumors. So being able to model how biological fluids flow and how different species are transported in the body is becoming an essential part of modern disease research. This is especially true for understanding how cells sense forces, that is mechanotransduction, and how different control mechanisms work in the human body. Such models also provide powerful tools for designing and improving drug therapies and delivery systems. Examples include intravenous thrombolysis for treating strokes and targeted delivery of cancer drug to tumors. With the growth of medical imaging technologies, we can now gather more detailed information about anatomy and blood flow directly from patients. This provides realistic data for setting up our computational fluid dynamics models, that is CFD models. When combined, these computational models have the potential to be used directly in diagnosis, surgical planning, therapy optimization, and even predicting treatment outcomes for patients. In this course, we will see practical examples of these models in action. A special lab demonstration using ANSYS Fluent will show how CFD can be applied to study blood flow through a bifurcated artery, helping us understand key flow features related to cardiovascular disease. So it is my great honor to introduce Professor Yun, who is a distinguished international expert for this Gyan course. So Professor Yun is the director of the graduate school and professor of biofluid mechanics in the Department of Chemical Engineering, Imperial College London. She has made pioneering contributions in the field of computational modeling of biological systems, with a special focus on blood flow, clot formation and lysis, and drug delivery in tumors. So her academic journey began with a BSc and MSc in thermofluids engineering from Dalian University of Technology, China, followed by a PhD in mechanical engineering from City University, London in 1992. Her research bridges engineering, medicine, and computational science, helping us better understand cardiovascular disease and improve therapies such as stroke treatment and cancer drug delivery. Professor Yun has received prestigious awards, including the Imperial College President's Medal for Excellence in Research Supervision and the Professional Engineering Publishing Award for Outstanding Contributions in Biomedical Engineering. She has served on several international editorial and advisory boards and continuously lead major projects funded by the British Heart Foundation and Heart Research UK, focusing on digital twins, aortic dissection repair, and AI-assisted biomechanics. Over her career, Professor Yun has supervised many successful PhD students and continues to inspire the next generation of researchers in biofluid mechanics and mathematical modeling. So we are delighted to have her with us for this course, and I warmly welcome Professor Yun for this Gyan course.
Thank you very much for the kind introduction. Thank you. Thank you very much.
Professor Dinakaran from the Department of Mechanical Engineering. So my research area is computational fluid dynamics and heat transfer. So I mainly work on fluid flow, heat and mass transfer in porous medium, drug diffusion studies, and microfluidics. So I welcome you all once again for this Gyan course on biofluid mechanics, mathematical modeling and challenges. So this course will run for 3 hours in the morning every day. So mostly from 10 a.m. to afternoon 1 o'clock. On the last day, we will have a demonstration session in the computational fluid dynamics lab. Thank you all. Thank you, Professor Yoon.
Thank you. Thank you very much, yes. So it's very exciting for me to be here to do these, deliver these short tours. This is my first visit to India, so everything is very new, very exciting. Well, I hope you'll learn something new in the next few days. Can I just ask for a show of hands, how many of you are doing PhDs or postdocs? So quite a few, right, okay. So the rest of the audience, I can assume you're doing a master program or in the Bachelor BTech program, right? Thank you. Now, my assumption is that you have learned some of the basic fluid mechanics and the mass transfer in your undergraduate program, is that right? So I'm not going to go through a lot of the fundamentals, but for the first day, I'm just going to summarize. So here's the outline. What we'll cover today are the fundamentals, biofluid mechanics, and biotransport. So I've got a few topics to cover. And first I will just have a refresher of the basic principles of fluid dynamics that we're going to use during this course. And then we will look at the physical properties of blood and non-Newtonian models, because some of you probably know that blood is a non-Newtonian fluid, so it's important to understand its rheological behavior. And then I will use an example, which is a well-known paper available in the literature, and I will go through that with you. And it's described two-phase model for blood flow in small vessels. And then we'll go on to look at oscillating flow in cylinder tubes, because we know that blood flow is not steady. And there's a well-known Wimley solution. Some of you are probably familiar with that. We'll go through the theoretical part of the Wimley solution and see what we can get from that. And then we look at the typical pulsatile pressure and flow waves in large arteries. We'll finish off with an example of the Murray's law. Some of you probably know that already. And then in the second part, we're going to cover the basic principles of mass transfer. So these will involve the convection diffusion reaction equations. Now these are important to understand mass transport in the cardiovascular system and also drug delivery. And then we will just touch on the fluid flow in tissues and a little bit on the porous medium, flow in porous medium, because biological tissues can be treated as a porous material. And then as an example, we're going to look at oxygen transport in the body and then study the famous cross-cylinder model of oxygen transport in tissues. So everything today are relatively fundamental theoretical, so I'm not going to show you any computational models for the first lecture today. And tomorrow we're going to look at the computational models for blood flow and the transport in the cardiovascular system. Okay, just to make a start. Now, because I don't know your background, and I'll give you a very, very brief introduction of the cardiovascular system, the circulatory system that we're interested in. So we all know that the important part of the cardiovascular system is the heart. And the heart is divided into the left and right side. So the circulation starts from the left side of the heart, and blood is pumped through the left ventricle, through the aorta, to the rest of the body to provide oxygen and nutrients to tissues and organs throughout the body. And then the oxygenated blood returns to the right side of the heart through the venous system, and then it gets pumped into the lungs through the pulmonary circulation, where gas exchange takes place. So then the blood that is rich in oxygen is returned to the left side of the heart through the pulmonary veins and ready for another cycle. So the whole cardiac cycle completes within about a second, depends on your heartbeat. If your heartbeat is about 60 beats per minute, then the cycle is 1 second. If your heartbeat is faster, then the cardiac cycle is less than a second. From a fluid mechanics point of view, it's quite interesting to know that the two sides of the system, the arterial system and the venous system, operate at very different pressures. So on the arterial side, the average pressure is around 120 to 125 millimeters mercury. And we know that if you take a blood pressure measures, you have a systolic and diastolic blood pressure, right? And then when it returns through the venous system, the blood pressure drops, and this is roughly about 25 mmHg. So the system operates in this way. Right, so some motivations about studying blood flow and mass transport in the cardiovascular system. And this is atherosclerosis, is a common disease. So these cartoons taken from the literature describe the development of atherosclerosis and the roles of the blood flow, especially shear stress in this process. So if we look at the cartoons on the left, we know that, so this is a diagram of blood vessels, and we know that the blood vessel actually is a multi-layered structure, and it has endothelium, which is endothelial cells, in direct contact with blood. And then we have the intima media adventitia in the blood vessel wall. And the development of atherosclerosis starts from accumulation of lipids in the subendothelial layer of the arterial wall. Because we know that the blood carries a lot of cells and other proteins. And for example, we have red blood cells, white blood cells, platelets, and also have dissolved proteins like the cholesterol, the fats, and lipids, right? So especially if the low-density lipoprotein or oxidized low-density lipoprotein, LDL, get permeated between the endothelial cells and through the endothelium and get accumulated in the subendothelial layers, and then these can accumulate and grow and make the wall thicker. So over time, the vessel become harder and stiffer, and if this is known as a plaque. So if the plaque grow, it can grow into the lumen, and so that limiting the cross-sectional area where blood flow can pass through. And then if this grows to a certain size, it will significantly impair the blood supply to the distal vessels. So now there have been many years of research in trying to understand the role of hemodynamic, and especially the shear stress exerted on endothelial cells by the flowing blood in this process. So on the cartoon on the right, and then you can refer back to these well-known Nature paper describing the development of the disease and also the role of blood flow, and which highlighted the importance of low shear stress and also the high shear stress and their involvement in the disease process. So this understanding, this fundamental understanding, had motivated a lot of research in this area and trying to understand blood flow and quantify for shear stress in particular. So now I'm going to start with the basic concept of fluid mechanics. So I'm sure that most of you know this already. I just want to familiarize with some of the terms that we're going to use. So first of all, we're going to assume that we're going to treat the blood as continuum fluid. So to treat the fluid as a continuum, it needs to satisfy the continuum hypothesis. And there is a well-known number, it's called Knudsen number. So the Knudsen number is defined as the ratio of mean free path molecules to the characteristic length scales. And typically, if the Knudsen number is small, is less than 0.1 for gas flow, then the continuum assumption is valid. Even though for liquid flow, this has not been well defined, but for the time scale that we are interested in this course, it is safe to assume blood as continuum fluid because we're not looking at the molecular modeling flow at a molecular level. And there are a few parameters that we're going to refer to fairly frequently. So we describe the fluid motion, visualize the flow using velocity field. This can be in Cartesian coordinates or cylindrical coordinates. And then in the Cartesian coordinates, the velocity vector is a function of x, y, z, and it's also a function of time. So this can be described using velocity components in each of these directions. And we can also work out the volumetric and mass flow rate. The volumetric flow rate is just the integral of the normal velocity over the cross-section area. So it gives you the volumetric flow rate. And if you multiply the volumetric flow rate by the fluid density, you get the mass flow rate. To visualize the flow field, we very commonly using streamlines, for example. So streamline is a pair of tangential to the velocity vectors. And here is a diagram of the 2D flow, where if you have a resolved velocity field in velocity vectors, then you can work out the streamlines using this analytical function. And we also describe flow using particle trajectories or path lines sometimes. So the trajectory, it follows individual fluid particles as they flow from one body to another. So there are differences between streamlines and path lines. However, if we assume the flow to be steady, so sometimes we say that the flow is steady, and the steady flow means that at each time point in the fluid, velocity is constant in time. And then in this case, the path lines and the particle trajectories and streamlines are identical. And we also sometimes say that the flow is unidirectional. And when we say unidirectional, it means that all motion is in the same direction. And then the streamlines in this case are parallel and straight. And there are basic dimensions that we use. These are the length, time, and mass. So if you see these symbols, sometimes if I use these in equations that I do not define, they mean usually L is the length and time is the lowercase t, and the mass is m. And F is obviously the basic dimension of force, and that can be related to the mass, length scale, and time. Okay, so these are all the very basics. Now we can move on to look at some fluid mechanics quantities, for example, fluid viscosity and the Newton's law of for viscous fluid. So here we define shear stress. Shear stress is a product of dynamic viscosity and the shear rate. So here the mu is dynamic viscosity. The dynamic viscosity is for Newtonian fluid, the viscosity is constant. And we sometimes also use the kinematic viscosity. Kinematic viscosity is usually denoted by nu, and that is just the ratio of the dynamic viscosity to the fluid density. So again, for the Newtonian fluid, that the kinematic viscosity is also a constant. And usually for most of the commonly encountered fluid, like water and gases, and they're treated as a Newtonian fluid because their viscosity does not change with shear rate. However, for biological fluids, and in fact most of the biological fluids are actually non-Newtonian, that means their viscosity is not constant. It changes not only with temperature as other fluids do, and it also changes as a function of the shear rate. So just give you a few, So maybe we'll talk about the different non-Newtonian behaviors in a minute. But first, to just look at another important parameter that we refer to in fluid mechanics. Everyone knows about the Reynolds number, right? So the definition of Reynolds number, and then the Reynolds number is defined as the inertia to the ratio of the inertial force to viscous force. And so this is the basic definition. So it requires the viscosity of the fluid, the density of the fluid, the average velocity, and also the length scale. So if we talk about flow in a pipe, in a cylindrical pipe, the characteristic length will be the diameter of the pipe. Right? So we also know that it depends on the magnitude of the Reynolds number. If it's much, much less than 1, then the viscous forces dominate and the flow is said to be tripping flow. And if the Reynolds number is much greater than 1, then the inertial forces predominate. And then it depends on the exact value of the Reynolds number that the flow can be defined as laminar or turbulent. So here is a cartoon that I took from the website where it describes very well the flow patterns in laminar flow, transitional flow, and turbulent flow. So this is a simple experiment using dye that are different Reynolds numbers. So typically, for flow, steady flow in a circular tube, Newtonian fluid, that if the Reynolds number is less than 2,100, then the flow is generally regarded as laminar. And we know that for laminar flow, that there is a theoretical solution. So if the flow is fully developed, then the velocity profile is parabolic, and that is given by this equation. So if you read any basic fluid mechanics textbook, and you will find this solution where the theories allows you to calculate the entrance length required for flow to become fully developed into a parabolic velocity profile. So when we have a parabolic velocity profiles, the maximum velocity is at the center, and the maximum velocity is 2 times of the average velocity across the cross-section. Now, the Reynolds number can become higher. So if the Reynolds number is greater, usually greater than 4,000, then the flow is said to be turbulent. And we know that in turbulent flow, the fluid motion is chaotic, and it involves the random movement of eddies and vortices, and it's very hard to mathematically resolve turbulent flow fully. And turbulent flow is always unsteady because it changes over time. And so when we describe turbulent flow, typically using instantaneous velocities. So instantaneous velocity has 2 components. One component is the phase average velocities, and the other one is the fluctuating velocities. And then using the fluctuating velocities, one could calculate turbulence kinetic energy and other turbulence-related parameters. Now, if a turbulent flow becomes fully developed, and again, if the flow is in a circular straight tube, then the velocity profile, a fully developed turbulent velocity profiles, can also be described as follows these power law profiles. You can see that, so this the exponent in the power law has been defined in the literature. So this could be n equals 7 could be a good approximation. And then this is what a turbulent flow would develop in a straight circular pipe, and this is a power law profile. You can see that the profile is much flatter compared to a fully developed laminar flow, where the profile is parabolic. And then in between laminar and turbulent flow, there is also a flow regime known as transitional flow. So the laminar to turbulent transition is actually very difficult to mathematically solve. So here I refer you to a well-conducted study published in the Journal of Fluid Mechanics, OJA, and this was published some years ago. And they did optical experimental study with a channel, and then there is blockage. So this represents a stenosed vessel or stenosed artery in the context of blood flow in the cardiovascular system. So they're trying to quantify, looking at visualizing flow in the channel downstream of this narrowing. And because of these contraction in area, so that the flow that passes through this narrowing, even though that the flow enters the channel, is laminar, but when it passes through the narrowed area, narrowed section, then the flow starts to accelerate, and then that creates a jet. So initially, there is a stable jet, and then this jet starts to break down, and then that gives rise to a transitional region, turbulent region, and then if the channel is long enough, then the flow becomes relaminarized again further downstream. There is very well description and velocity profiles shown in the original paper. So if you're interested in laminar to turbulent transitions, which is a flow status encountered in the cardiovascular system, I would refer you to read these classic studies first. Right, so now how do we describe flow in 3 dimensions? So the basic equations, and again, I assume everyone knows, learned these in your basic fluid mechanics. So I'll just go through these very quickly. We have the governing equations. The essential equations are the mass conservation equation and the conservation momentum. The mass conservation basically describes what comes into the control volume goes out to the control volume. So for incompressible flow without chemical reactions, then and also for the dynamic fluid, this can be described using mathematically using these equations. Divergence of the velocity equals to 0. If you express these mathematically in 3-dimensional Cartesian coordinates, and they can be expressed like this. So the next one is the conservation of momentum. And again, for incompressible flow with constant viscosity, we have the Navier-Stokes equations. Everyone knows about that. So this is acceleration, this is convection terms, and then the force term, including, usually we consider the pressure gradient and the viscous force, and also the gravitational force or any other external force that is relevant to the problem that we solve. And again, in the Cartesian coordinate system with coordinates x, y, and z, we can express the Navier-Stokes equations because if we treat the problem as 3-dimensional, then these represent 3 equations. So we have momentum balance in each of the x, y, and z direction. Right, so obviously these are the partial differential equations, and then these equations need to be solved numerically using numerical techniques, which we will discuss tomorrow. So first, let's look at the physical properties of blood. Well, we know that blood is a viscous fluid, and it's a mixture of plasma and blood cells. And typically, the plasma occupies about 55% by volume of the blood, and the rest of 45% are cells. So if we look at the plasma composition, well, in fact, it's mainly water. So 90% of the plasma is water, and it also has the rest are the dissolved proteins and also salts. So the physical property of the plasma is very close to that of water. Density is slightly larger than the density of water, and viscosity also slightly larger than the density of water. Now let's look at the cellular components. So for the other 45% of the blood, that it contains red blood cells. Now red blood cells actually are the most abundant type of the cells in blood. It comprises about 95% of the cell volume. We all know about its important role. Red blood cells is very important. The main role is to transport oxygen through the hemoglobin contained within red blood cells. And their normal shape is like a donut with a dimple in the middle. And the diameter is approximately 8 microns. And the other cells are the platelets and the white blood cells. And we know that the platelets, well, these platelets takes up approximately the other 5% of the cell volume. And its main function are in the blood coagulation and hemostasis. So it's quite important. And the shape depends on whether the platelets is in resting or activated states. If they're resting states, it looks like this, and if they're activated, they look like they have hands like this. And the typical diameter is about 2 to 3 microns. We also have some white blood cells. So in the context of this lecture, the size of the red blood cells, and we're also going to touch on the platelets. We're not going to model white blood cells. Right, because of the presence of the cells occupying about 45% by volume of the blood, that they will have a role, they will have an influence on the blood viscosity. So as a result of that, the whole blood, we talk about whole blood, that the density is roughly about 1055, and then this is more than that of water, and this is density at normal body temperature, 37 degrees, and the viscosity is roughly about 3 to 4 times 10 to the minus 3. And this is when the shear rate is high, when the blood starts to behave like Newtonian fluid. But because the exact value depends on the hematocrit. So the hematocrit levels varies from individual to individual, so depends on whether it depends on the health status of the person. And viscosity also change with temperature and also the shear rate, as blood is a non-Newtonian fluid. So very briefly, if we look at the non-Newtonian fluid, so generally speaking, there are different types of non-Newtonian fluid, depends on how the viscosity change as a function of the shear rate. So plotted on this schematic diagram, and these are the shear stress and plotted as a function of shear rate. So first we have this straight line. This corresponds to Newtonian fluid when the viscosity is constant. And then for some fluid, for non-Newtonian fluid, that the viscosity changes as a function of the shear rate. So for instance, the pseudoplastic fluid, and this is quite common, is also known as the shear thinning fluid. In this case, that the viscosity will decrease as the shear stress the shear rate increases. So at low shear rate, that the viscosity is high. At high shear rate, that the viscosity is low. And blood is an example of shear thinning fluid. And there could be other type of fluids represented in this diagram, but we're not going to look at other fluids. Just know that blood is a shear thinning fluid. That should be sufficient. And there is also yield stress, and which means that the fluid will not start to move until the shear stress exceeds a certain threshold. So blood is also exhibit yield stress. So now, how can we describe these mathematically? And there are various models that have been introduced in the literature that can be used to describe the non-Newtonian behavior of blood. The most common one is not just for blood, but for other non-Newtonian fluid, is the power law model. So the power law model says that the magnitude of the shear stress is related to the shear rate to the power of n. And then very often that we describe an apparent viscosity. The apparent viscosity for non-Newtonian fluid is simply defined as a ratio of the magnitude of the shear stress to the magnitude of the shear rate. So as described over here. So it depends on the type of non-Newtonian fluid that if n equals to 1, then these describe a Newtonian fluid. So these power law reduce to the Newton's law of viscosity. And then if n is less than 1, for example, when we describe the property of blood, then it's a shear thinning fluid. And then for shear thickening fluid, then n is greater than 1. Now we also talked about yield stress. So a basic model that describes non-Newtonian fluid with yield stress is the Bingham model. Then you can see that there is a presence of the yield stress in this model. But these can be combined to describe the behavior of blood. So these are the various models that have been used in the literature to describe the non-Newtonian behavior specifically of blood. So the Casson model, you can see that it accounts for the yield. Well, in fact, all of these models account for yield stress and the shear thinning behavior of blood. So when you need to use one of these models to describe the blood behavior if you're going to build a mathematical or computational model to solve the blood flow in the cardiovascular system, you can choose any of these models. There are also different variants of the current model. The Kimada model is quite commonly adopted, and it's also used in some of our published work. It's a function of the hematocrit, and you can see these various constants. These have been determined, so like K naught, K infinity, and also gamma critical shear rate. And these have been determined experimentally based on experimental curves of the viscous behavior of blood. So here you can have sort of a visual comparison of the different models. So if we look at the figure on the left, we plotted the viscosity as a function of the shear rate. So first recognize is this red horizontal line. This corresponds to a Newtonian fluid, so the viscosity is a constant, it doesn't change with shear rate. But then if you use any of the other models that I showed on the previous slides, and then you can see how they compare with the Newtonian fluid. And they all exhibit the same behavior. For example, when the shear rate is low, that the viscosity is high. When the shear rate is high, the viscosity is low. And all of them will plateau at high shear rate. So typically, if the shear rate is greater than 100, I think this plot is about 1,000, that they will plateau to a value that is close to a Newtonian fluid. So it depends on what value that you assume as a Newtonian fluid, then they can converge to different levels. So obviously these curves are created for a given hematocrit. So if you've used different hematocrit levels, then the curve will move up and down a little bit. And then if you look at the behavior of whole blood, so on the right of your slides, we can see the viscosity. This is the viscosity curves as a function of shear rate for whole blood. So if you just look at the red curve, and this corresponds to whole blood, normal, represent normal blood, and you can see how its viscosity changed as a function of shear rate. So in this expression, that when the shear rate, again, when the shear rate is high, that the behavior of the viscous behavior of blood tends towards a Newtonian fluid, and that is why in a lot of the computational studies of blood flow, that the blood has been, especially in the large vessels, when the flow rate is relatively high, then blood has been assumed as a Newtonian fluid. And the justification given by the researchers is that the shear rate is high, and then when shear rate is high, that the blood behavior it can be approximated as a Newtonian fluid. However, that's not the case when you're interested in, or when you look at the blood flow in small vessels. If you look at the small vessels, so when we talk about small vessels, we mean that their diameters are usually less than 300 microns. So for blood flow in small vessels, the blood rheology is strongly influenced by the two-phase nature of blood. So because we said that about 45% of blood contains cells, so the cells, the interactions, the relative motion between blood cells and the plasma, the fluid, will cause a different effect. And so the well-known first linguistic effect, which says that the apparent viscosity decreases with decreasing diameter, and these are for vessel diameters between 30 and 300 microns. So for very, very small vessels, smaller than 30 microns, the behavior is even more complex. And the reason for that is because the red blood cells, they're actually relatively, the size are relatively large compared to the tube diameter when you look at very small vessels. So for the red blood cells of an approximate diameter of 8 microns, and that could be quite significant if you look at the vessel diameters of around 20 microns or 30 microns. So if you look at the blood flow in very, very small vessels, the presence of individual cells must be accounted for. But if we look at vessels that are greater than 300 microns in diameter, then it can be, the two-phase nature can be neglected, and the blood is treated as a single-phase fluid, continuum fluid. So if you're interested further into looking into the details about how the blood behaves in small vessels, I would refer you to this paper published in 2005. So I've extracted this figure from that publication. And there's a lot more you can learn from that paper. Right, so just to come back to the fundamentals of fluid mechanics, and as we're talking about blood flow in maybe small vessels first as an example. So look at the non-Newtonian model for blood flow in small vessels. And then we look at the Priest model. So the Priest model describes the behavior, and the curves I showed on the previous slide pretty well. So if you look at the Priest model, mathematical expression is given here. And you can see that the viscosity is a function of the hematocrit. It's also a function of the vessel diameter. And then so these need to be used in conjunction with the other two equations. And the various parameters can be found in the literature. And then the exact, some further details, theoretical details about this model and the corresponding experimental data can be found in the original paper by Priest. And this model is widely used by researchers in the research community when I look at blood flow in small vessels. And we have used the Priest model in our work in modeling blood flow distribution and oxygen transport in the retinal circulation in the eyes. Because when you look at the small vessels in eyes, their diameters are much smaller compared to the large vessels in arterial systems. So we've used the Priest model in the past. Right, okay. So now we just go through very briefly an example before the break. So this is blood flow in small vessels. What this theoretical paper published in Biorheology in 2001. I'll refer you, so if you use the citation details, you can find the original paper. So I've extracted some of the basic equations from that paper just to take you through how the fundamental equations can actually be applied to look at, theoretically, to look at blood flow in small vessels and then how they actually relate to the Priest model. So in this paper, the interest of the tube size is in the range of about 20 to 300 microns, so these are small vessels. And because of the size of the vessels, that the presence of the cells, especially red blood cells, need to be considered. So in this well-known theoretical work, we described the two-phase model for flow, that they divided the flow region inside the channel into two zones. And one is the core. So this is the core. And within the core, it contains red blood cells, and it has an effective viscosity of mu. The subscript C represents the core. And then there is also the surrounding area, the peripheral area near the wall, is described as a cell-free layer. So the cell-free layer contains plasma only, and it has the effective viscosity of mu is not. So to separate these two, in the two zones, the viscosity, the fluid viscosities are different. So in the core, in the center, have red blood cells, and in the peripheral areas, it's cell-free. So then, if you consider idealized scenarios for flow through a strict cylindrical tube, then we can actually apply the Navier-Stokes equations for each of these regions and then solve that. So here, and again, I copied the equations from the paper, so you can look at the paper for further details. So first, that for the central core region, where it contains red blood cells, we can use the Navier-Stokes equations in the cylindrical coordinate system. And also, if we ignore the gravitational force and assume the flow to be steady, and then we can reduce, the equation is reduced to this form. And similarly, that for the cell-free layer, we can also write the same equation, but the only difference is that the fluid properties are different. So the fluid in the cell-free layers does not contain red blood cells, where the fluid in the core has red blood cells. So they have different density and viscosities. So that needs to be accounted for. Now, these two equations, you can actually solve these equations mathematically without using any numerical computational tools. But before you solve the equations, you also need to apply the appropriate boundary conditions. So for this case, that because the geometry is symmetric and the flow is assumed to be symmetric, that we have the symmetry condition at the center. So at the center of the vessel, that we have mathematically described the symmetry condition. And then we also have the no slip condition at the wall, because the wall is assumed to be rigid, velocity 0, right? So that's two equations. And then we need another two equations to solve theoretically the Navier-Stokes equation. So here, at the interface between the cell-free layer and between the cell-free zone and the core region, that we have continuous velocity. And then we also have continuous shear stress. So these are mathematically described. And then if you apply all these boundary conditions to the equation that we mentioned earlier, mathematically you can solve the velocity profiles as a function of the radial position in each of these zones. So these are the solutions. And again, these were taken from the paper. So if you need more details, I strongly recommend you to read the original paper. And then to simplify these expressions, that they've normalized the radial positions and a few other parameters, and then so that the solution can be expressed in a slightly more compact form. And then once you worked out analytical solutions for the velocity profiles, you can integrate the velocity profile in the respective areas at each cross-section. You work out the volumetric flow rate. And then so that finally, after integration, and this is the final expression, so this is the volumetric flow rate. And then in the original paper, then they also relate, you can relate the derivations and derive it further and relate that to the plasma layer thickness, and also, so plasma layer thickness as a function of diameter, and how it varies. And then you can relate these to the derivation with the Chris model that I described earlier. So for the sake of time, that we don't have time to go through this in detail, but I would recommend you to go through the original paper to study this further. I think that's probably appropriate time for a break, and then we will start looking at the oscillating flows. You can hear me well? Yeah, good. Yeah, so in the second part, we're going to first look at some theoretical solutions for oscillating flow in a cylindrical tube. So here again we have a lot of assumptions. And we assume that the flow is fully developed in a straight cylindrical tube. So the tube is long enough and the velocity does not change in the direction of flow. So the velocity is only a function of time and the radial position. And we assume the fluid is Newtonian, and the pulsatile flow is driven by a sinusoidal pressure gradient. So you see the pressure gradient here, and this can be described as a cosine function here. And mathematically, it's convenient to describe these using complex numbers. And we also need to make use of the angular frequency when we look at the change of the velocity profiles as a function of time. And angular frequency also appears in this expression. Right? So this is the Navier-Stokes equations. It's reduced to this form when we made all of these assumptions. And again, these can be solved when combined with the pressure gradient described in that expression. Now, this equation was solved by mathematician John Winsley. At one point, I think it was actually based at Imperial College London. And so he solved those equations using these boundary conditions. We have symmetry, so the commonly that if we have a cylindrical tube, then we have the symmetry condition. And this, as it's a rigid tube, we have no slip condition at the wall. So apply these to that equations, and then mathematically, a solution is actually found. So the solution is expressed over here. You can see that velocity is a function of the radial position. The radial position appears here. This is a normalized radial position, normalized with respect to the radius of the pipe. It's also a function of time, so time is over here, lowercase t. Now, in this solution, it involves the Bessel function. So this is the Bessel function, the first kind of the order 0. And mathematically, the Bessel function is expressed like this. So with this given solution, one can actually make use of MATLAB or some other tools. You can solve the equations so that you can find the actual velocity profile. Right, so this is how visually the velocity profile look like. So you can see that because the pressure gradient is time dependent, it varies over time, so that the velocity profiles is also a function of time. And then in terms of the shape of the velocity profiles, it's no longer parabolic. It depends on some of the dimensional parameters that we will describe in the next slides. That typically it can have M-shaped or W-shaped velocity profiles. So this is just a typical example of the sinusoidal velocity profiles at a particular frequency. So if you look at the dimensional parameters we're interested in, and here we use a symbol alpha to denote the Wimmer's number. So Wimmer's number is very often referred to when we describe blood flow in the cardiovascular system. And so this is defined as the ratio of angular frequency to kinematic viscosity. It's also a function of the size of the radius. And here we introduce another symbol, uppercase T. This is the fundamental period of the oscillatory flow, or known as the pulse period. So you can see that it measures, the Wimmer's number measures the ratio of the unsteady emitter effect to viscous effect. And then if the Wimmer's number is low, it means that it represents low frequency of pulsation, and so that the flow tends to a steady flow. And then if the Wimmer's number is large, it's high frequency pulsation. And when we describe pulsatile flow, we need to make use of Wimmer's number as well as Renn's number to consider the dynamic similarities of pulsatile flow. So here I set the numerical solutions of the equation that I described earlier, the Wimmer solution, and this can be established using MATLAB. You can also calculate the velocity profiles as a function of time for different Wimmer's number, and just to appreciate how the frequency of pulsation can affect the shape of the velocity profiles. In the next slides, I've got a few representative profiles, and this was taken from a textbook. So if we take from the left to the right, we have alpha about just over 3, and then we gradually increase alpha to somewhere about 6.67, so it's twice as big as over here. And you can see already how the velocity profiles can change with Wimmer's number. And then so this typically these M-shaped velocity profiles, and then these W-shaped. So this one is fairly close to the one that I showed you in the animation. And then as you increase, the velocity profiles become slightly flatter. So because we have a mathematical expression of the velocity profiles, and we know that if we integrate the velocity profile over a cross-sectional area, we get the volumetric flow rate. So mathematically, the volumetric flow rate is obtained by integrating the velocity the solutions for the velocity profiles, and then over a cylindrical surface area, and then we get a cross-sectional area, and we get expression for the volumetric flow rate, and that involves the use of a vessel function for order 1. So again, you can program these in MATLAB to calculate the volumetric flow rate, and to find the interesting thing is you can find that the volumetric flow rate and the relationship with pressure gradient. And so I think it's in the next slide. So here I've got plots of pressure gradient. So this is the green line corresponds to the pressure gradient, whereas the blue line corresponds to mass flow rate. And this is plotted for Women's parameter equals to 6.67. And already you can see that there is a phase lag for the flow. And so that the flow peaks behind the peak of the pressure gradient. So it's quite typical of this oscillating flow. And if you plot the phase lags, if you measure the phase lag and then plot it as a function of Women's number, and that's what you get on the right. So this is a phase lag expressed in degrees. So assuming that, using angular frequency, assuming that if one complete cycle is 360 degrees, so 90 degrees is a quarter of the cycle. And you can see that as you increase the Women's number, that the phase lag initially increased very sharply, and then it slows down, and then it plateaus. So the maximum phase lag is slightly less than about a quarter of a cycle. Now, if you want to know more about the Women's solutions, you can refer to the original paper published by Women's. It's quite a long paper, and it has detailed mathematical solutions contained in that paper. So, just a brief summary. What we have seen from what we have learned from the Women's solution is that the shape of the velocity profile depends on the Women's number, and it varies with time or phase. And the velocity is not in phase with the pressure, except for very low Women's number. Now we see that there's M-shaped and W-shaped velocity profiles because of the inertial force. So what we meant by inertial force is that the change in the flow is driven by the sinusoidal pressure gradient. And initially, the fluid in the center at the core of the pipe has a high inertia, so it takes time for the high inertia fluid to change, whereas the fluid near the wall has relatively low velocities and low inertia, so it's faster to respond to the change in the pressure gradient. And then these describe the extremes of values, behaviors. And then when alpha increases, you can see that inertial effects dominate, and this gives rise to the MW-shaped velocity profiles, and the phase shift increase with alpha. And also very high values of alpha. The velocity profile is relatively flat. Maximum velocity happens near the wall rather than at the center of the pipe. And the mean flow lags the pressure gradient by almost a quarter of the cycle. Right, so these are theoretical solutions for oscillating flow that follows driven by a sinusoidal pressure gradient. If we want to relate that to the reality, when we think about or look at blood flow in the cardiovascular system, we know that the flow is pulsatile because as the heart contract and expand, the blood flow accelerate and decelerate, right? So the blood is like a pump. It drives the acceleration of the blood flow through the left ventricle into the aorta and to the rest of the body. So there is a pressure wave propagation through the arterial systems, and then there is also the corresponding flow waveforms. And these waveforms, these were taken from a textbook by Carroll et al. This is the mechanics of the circulation. And these describe the pulsatile pressure and flow waveforms along the aorta at different locations. And these were measurements. These were actually measurements made in animals at the time. And then we can see that it obviously changed. So, so this one is this set of waveform. One is the pressure. The total one is the pressure. This is the pressure waveform, and this is the flow waveform. You can see that as you move along the aorta, this one is the ascending aorta, close to the heart. As you move along the aorta, further down in the chest, this is in the descending aorta, the corresponding pressure and the flow waveforms. You can see that the pressure waveform and the flow waveform actually change along the aorta. And further down, this is again in the descending aorta, further downstream, and this is in the abdominal aorta, and you can see the corresponding pressure and the flow waveform, and they're quite different from the pressure and flow waveforms in the ascending aorta. Now, obviously, these waveforms, especially the pressure waveforms, is not theoretical, it's not sinusoidal, right? So that's one difference. And the other difference, if we extract these pressure and flow waveforms from here into these diagrams, and we can see how the pressure waveform change along the aorta from the vessel that is closest to the heart to somewhere in the leg. So this location, A, is in the ascending aorta, somewhere over here, whereas location E is in the saphenous artery, is actually in the leg, somewhere further down. That's not shown. Right, so the pressure waves, we can see some changes. Even though these waveforms were taken from animals, but they, in human, the behavior is very similar. The pressure, the peak pressure become higher. So the peak pressure increases from the ascending aorta down to the saphenous arteries, whereas the peak flow actually decreases. So the reason for the pressure to increase is because of the compliance of the vessels. So the arterial walls is compliant, it's not rigid. And the vessels that is closest to the heart are more compliant compared to the vessels further away from the heart. And so that contributed to these change in the pressure waveforms. And in terms of the flow waveforms, and this is because of the mass conservation, because the branching of the aorta, right? So as the flow passes through the ascending aorta into the arch, it gives off branches. So these branches, some of the portion of the blood flow, typically about 15 to 30% of the blood flow will exit through these vessels to feed the blood vessels in the shoulder, to the arms, and to the head. And then it continues to branches. There are smaller branches that are not shown here, and then there are further branches into the renals to fit into the kidneys, other major organs in abdomen, and then bifurcate into the legs. So as the blood vessels branches off, that some of the blood is diverting into other parts, and so the flow is reduced when you look at a single vessel further downstream in the leg. So that's why the velocity decreases. So here I've summarized the behavior that we observe. So we've seen the pressure rises, and the shape of the pressure waveform becomes steeper as it travels from ascending aorta to the femoral arteries, right? And we also see that velocity falls gradually due to successive branching of the main arteries. And an interesting thing is, if you look at the velocity profiles, the waveforms, the flow can be reversed during part of the cycle. Right, so this is the reality. This is what the pressure gradient and the pressure looks like in the, apologies for the labels. I think I should have the labels before, but somehow it disappeared. This shows the typical pressure and the pressure gradient curves, right? So the pressure curve is the upper curve, so this resembles the pressure curve that we saw earlier. This is a representative pressure wave corresponding to a given delta, and then this is the corresponding pressure gradient. So obviously this is not a sinusoidal waveform, but however, this can be mathematically decomposed and then expressed as a sinusoidal form. And then we can work out the corresponding flow rate. So the pressure gradient is here. So first we express the pressure gradient using this form. And the corresponding velocity profiles can also be found similar to the Wimley solution. So this is the analytical solution corresponding to the velocity profiles as a function of the radial position and time. And this is the velocity profiles with so this is the actual expression of the velocity profile. This is a solution. So this is equivalent to the Wimley solutions for oscillating sinusoidal pressure gradient driven flow. Right. So we can see that if alpha tends to 0, then the flow tends to steady flow, and then these form will actually approach the quasi-static limit. And then if the Wimley's number is very large, then it approaches this the limit, which is driven by very high frequency pulsations. So theoretically, you can analyze, you can find the theoretical solutions for flow that correspond to physiologically realistic pulsatile pressure waveform. And likewise, you can integrate the velocity profiles over a cross-sectional area to obtain the volumetric expression for volumetric flow rate. And then again, one of the parameters that I mentioned earlier, which is quite interesting and play a significant role in the development of aspergillosis or other arterial diseases, is known as the shear stress, especially the shear stress at the wall acting on endothelial cells. So the wall shear stress can also be derived by differentiating the resolved velocity profiles and then so the velocity gradient multiplied by viscosity. If we assume blood behaves as a Newtonian fluid, you can have the Newtonian viscosity here. And then you can find a mathematical expression for shear stress. So all of these can be analyzed, and then if you have access to MATLAB or other tools, then you can plot looking at the relationship between shear stress, flow, and pressure. So this is what the corresponding flow waveform look like. So this is, well, sometimes we don't have, especially in applications, we don't have the pressure waveform, but if we have a Doppler ultrasound measurement, we have a flow waveform. So if we start with the flow waveform, and again, we have decomposed the flow waveforms into this expression, then the corresponding velocity profiles can also be found. So this is the velocity profiles that correspond to a realistic flow waveforms. And graphically, this is what the velocity profile looks like. Well, even though the flow and pressure waveform are not idealized, but we can see that the velocity profiles, they still have some of the features we observed from the Wimley profiles. For example, the W-shaped or M-shaped velocity profiles are still present. Okay, so here's a summary of the assumptions and limitations of the Wimley solution. So first, the flow is assumed to be unidirectional, so it's one direction in the axial direction only, and the flow is assumed to be laminar, fully developed, and the fluid is assumed to be Newtonian. And we assume that there's no interaction between harmonics when we look at a realistic pulsatile flow, and it gives an exact solution. So even though it may not be realistic, but it provides some basic understanding of pulsatile flow, and also can be extended to realistic physiological flow and pressure waveforms. Right, so at this point, as we're talking about focusing on blood flow, so I wanted to take you through Murray's law. Some of you probably know that already. And so Murray's law, it describes the flow and anatomical evolution of the vascular system and makes use of the flow mechanics, some of the basic equations that we learned at the very start. So the fundamentals, the idea of this original paper, I think there's a citation somewhere here. Murray developed these in 1926. The paper was published in PNAS in 1926. So if you can't find the paper, I can point you out. I have a copy of the Murray's original paper. So the hypothesis is that in mammals, that the vascular system is subject to two competing energy demands. So the first is the pumping power required to drive the flow through the blood vessels. So this is like for students studying engineering, we know that if you have a pump, then you need to have a driving force, so the pumping power, right? So the pumping power is related to the pressure drop and the flow rate through a pipe. Very similarly, to drive blood flow through blood vessels, we also have the pumping power required. And we can use the fundamental flow mechanics to write the pumping power required for this part. But because blood vessels are not engineering pipes, they're living tissues, and they provide, so the blood passes through the blood vessels, need to provide oxygen and nutrients to the cells and tissues throughout the body. There is also metabolic consumption, metabolic requirements from the blood. So it says that the other part is the power required to produce and maintain the volume of the blood itself, right? Right, and then he said the hypothesis is that the flow mechanics can influence the growth and formation of blood vessels, and such that the structure and organization of the branching tree in the vascular network actually follows energy minimization principle. So in other words, if you write the total energy required, the total energy demand by considering these two components, and then you solve a minimization problem following the minimization principle, that will give you an optimal vasculature that requires the least energy to make the system function. And so, if it follows that rule, and then the conclusion is that, so this is the well-known Murray's minimum energy hypothesis, and that is, if you consider a bifurcation, so bifurcation is the vessel branches into two branches, so we have a parent vessel that has a diameter of D0, D0, and then it gives out two daughter vessels, so with each has a diameter D1, D2, and it says that to follow the minimal energy assumption, that the diameters follows these cubic rules. Right, so how can that be derived? I've taken some of these through take you through some of this process, but again, if you wanted to know the full details, you can refer back to the original paper published by Murray. So looking at the cost function, so if you want to solve a minimization problem, first you write, or optimization problem, you write the cost function. So the cost function J, and that consists of two parts. The first part is the pumping power. So the pumping power required to drive blood flow through blood vessels. This is the product of the pressure drop and the volumetric flow rate. The second part is the metabolic demand, the metabolic requirements, and this is related to the volume of the blood. So the volume of the blood is given here. So A is the radius of the pipe, and L is the length of the pipe. And B is a metabolic constant, which obviously we assume is a constant, and then we solve this problem. Now, if we consider the flow to be steady, so that's a big assumption. Consider steady flow, unidirectional, so using all the assumptions that we've said earlier, then the pressure gradient can be expressed as a function of the flow rate. And so that this pumping power can be reduced into this form. And I think anyone during the first year engineer fluid mechanics will know that. When you solve a flow through pipe, you do this as well. So here is an expression just by replacing delta P with the expression for, we have the viscosity of the fluid, we have the volumetric flow rate, the length of the pipe, and the radius of the pipe. So here, we're going to solve the minimization problem of this function. And the assumption is that the length of the pipe is fixed, the volumetric flow rate is fixed, viscosity and metabolic constant are also constant. And then we can differentiate these with respect to the radius r. And then that's how mathematically each step works. So this is the differentiation of this equation. And if you set this equal to 0, you solve for that, and you find the radius to follow the volumetric flow rate like this, and then the volumetric flow rate is expressed as the cubic function of the radius, right? So now, so here is the solution of the minimization problem. If we apply these to the bifurcation problem, and then using mass conservation, so consider that a bifurcation. So for mass conservation, what comes into the mass flow rate or the volumetric flow rate enters into the parent vessel should equal to the sum of the volumetric flow rate exiting through the two daughter vessels, right? So we apply to that. Then we have the volumetric flow rate of the parent vessel equals to the sum of the volumetric flow rate in each of the daughter vessels. And then we replace this constant with another parameter k just to make it simple. And then we get this equation. And so that is equivalent to say that this state the Morris cubic law, right? So mathematically, it's fairly simple. What that means is that for the symmetric bifurcation, if the daughter vessels have the same diameters, then you can further simplify this, and it means that each daughter vessel diameter is about 0.794 times of the parent vessel diameter. And then you can also work out shear stress, because we have the shear stress here. I found it easier just to use a force balance, because the forces acting on the fluid, you have the shear stress, and shear stress multiplied by the surface area give you the force due to the friction force, and balanced by the pressure force. So pressure acting on pressure gradient acting on the cross-sectional area. So by using this expression, you can work out shear stress as a function of volumetric flow rate. So it's quite interesting that if you remember that after solving the minimization problem, the volumetric flow rate is related to the radius through this cubic relationship. Then you find that the shear stress is in fact just the square root of the B times viscosity. So B is the metabolic constant and mu is the fluid viscosity. If both of these are constant, and again that's an assumption, then the shear stress is constant, right? So it's interesting what it says is that for the formation and the evolution of blood vessels in the vascular network, that if the system follows the minimization principle, then the diameters should follow this cubic group. So this is highly theoretical. Is that true? Does it happen in reality? I think that some researchers have actually tried to see whether the natural evolution of the blood vessels in the vasculature actually follows the Morris rules. It actually applies to small vessels. So it does not apply to large vessels like the aorta that we looked at earlier, or the other large vessels. But for very small vessels, especially if you look at into the capillary vessels, the branching systems, actually is not far off from a cubic rule. And we have, in my group, we've done a study on analyzing the vasculature in the retinal network in the eye. And we found that the morphology actually varies quite a lot from normal people and also patients with high blood pressure, hypertension, or diabetes. So the vasculature actually changed. And then when we analyze the branching pattern of the small vessels in the normal eyes, it's healthy people in the retinal vasculature, it actually follows fairly closely to the cubic root. But if you look at the anatomical morphological structures of the retinal vasculature in patients with hypertension or diabetes, it deviates quite a lot from the cubic root. So it is interesting to note how our system actually evolved, the vasculature evolved, and then how it can be, to a certain extent, explained by Murray's work. Right, so I'll spend the next 15, 20 minutes or so on some basic concept of the mass transfer. So I've covered the very basic concept of fluid mechanics. So for mass transfer, the mode of mass transfer, we all know, we have molecular diffusion, and it can also have convection. So mass can be transported by convection due to macroscopic movement of medium, in this case fluid. The molecular diffusion follows the fixed law, right? So fixed law dictates that the molar flux of components of species I, this is proportional to the concentration gradient of that species. And the proportionality is known as molecular diffusivity of that component. And for the convective mass transfer, it is difficult to describe this theoretically, but generally speaking, that the convective mass flux is related to the concentration difference. So this is the concentration difference between one location and then the concentration difference in the surroundings. And then this is related to what is known as the mass transfer coefficient. Now obviously, to determine the mass transfer coefficient, one needs to use some of the empirical correlations that have been developed for different flow regimes. For example, one of those, if you consider turbulent flow in circular tube, I think that the students studying engineering degrees, engineering course, when you learn mass transfer, you'll be introduced to several mass transfer correlations, and heat transfer, just like heat transfer correlations. So for heat transfer, you have typically you have the Nusselt number. So Nusselt number contains the heat transfer coefficient, and that can be related to like the Prandtl number and the Reynolds number. Or likewise, the mass transfer, you have the mass transfer coefficient, and that is defined in the Sherwood number, and then so that can be related to the Reynolds number and Schmidt number. So this is just one of those equations commonly used in engineering applications. So some of the dimensionless parameters that is relevant to describing mass transfer in biological systems. So one is the pictet number. The pictet number is defined as the ratio of diffusion time to convection time. So diffusion time is determined by the characteristic length scale squared divided by the molecular diffusivity. And obviously, if the diffusion is fast, diffusion time will be short, right? So the pictet number will be small. So if the pictet number is very small, then diffusion is faster than convection, transport is diffusion dominated. And on the other hand, if the pictet number is much larger than 1, then convection is faster than diffusion, and transport is convection dominated. And other dimensionless parameters involves the Schmidt number. So that defines the momentum diffusivity to mass diffusivity. So purely, this can be determined by the physical properties. And so the picnic number can actually be related to the Renz number and Schmidt number. So these are some of the dimensionless parameters that are quite useful when we analyze a problem before you solve it numerically. So what I usually teach my students, so this is part of the course I taught to the final year, fourth year MA student at Imperial in chemical engineering and also master students. So when I taught them the mass transport part, I always ask them to initially, before they solve the problem, to estimate the Pickwick number and try to understand what is the dominant mass transfer mechanisms in the system to decide whether it's diffusion-driven or convection-driven, and then it can help them to simplify the problem. So the basic fundamental equation to describe mass transport is the convection-diffusion reaction equation. So this is a general equation. And then you can see that we have the convective term here, and then we have the diffusion term. So this is the diffusion, and then we can also count for reaction term here. And this is relevant when we talk about, for example, oxygen transport in tissues, because oxygen is consumed by cells, right? So there isn't reaction or consumption terms here. If we express these equation in 3D in Cartesian coordinates, this is a mathematical equation that we need to solve numerically. And also you can express the same equation in cylindrical coordinate systems if we assume a pipe as a cylindrical pipe. And again, you can simplify the equation based on understanding about the dominant mass transfer mechanisms. For example, if the flow is one-dimensional, and then if it's steady, and it's diffusion only, so in other words, there's no convection, no chemical reaction, and then the convection-diffusion reaction equation is reduced to this form. I'm sure that you've solved this equation as part of your coursework in your basic engineering mass transfer, and then you can find a linear profile of the concentration. And then if you assume that it has diffusion and also convection but no chemical reaction, then the convection-diffusion reaction equation is reduced to this form, and this form can still be solved mathematically. You can find an expression for concentration profile as a function of x, and then you will find that the shape of the concentration profile will actually depend on the magnitude of the Pickwick number. And another special case is if you assume that it's a steady-state diffusion with chemical reaction. If there's no convection, then this equation, you can solve this equation mathematically, right? And go on. You can assume, make other assumptions. For example, if the convection is much faster than diffusion, in some case that you might neglect the effect of diffusion. Right. So talking about the mass transfer, so we have mass transfer species within the blood in the system, but also mass transfer from the blood through the endothelial cells, because blood vessel walls is permeable to some of the proteins and oxygen. And so we need to consider flow through tissues. So most of the biological tissues, they contain, the biological tissue contain intravascular and extravascular regions, so inside blood vessels. So these are the intravascular regions and extravascular regions. And the extravascular regions, which contain cells and interstitium, and this can be considered as a porous medium for fluid flow and solid transport. So what you learn about the porous medium flow can actually be applied to analyzing flow in biological systems. And then if you couple those equations with the mass transport equations, then you can solve mass transport in biological tissues. So the simplest form to describe porous medium flow is actually the Darcy's law, which has been widely used in the analysis of interstitial fluid flow, when the size of the tissue is actually larger. So the size of tissue is at least 2 orders of magnitude larger than average pore size. So this is, we're looking at not at the cellular, not at the the cell scale, cellular scales, but looking at the organ level. You assume that it's a homogeneous and isotropic medium, then you have the dusty velocity can be related to the pressure gradient. And here you have the hydraulic conductivity, right? And then these can be, the hydraulic conductivity can be related to permeability of the porous medium, and then that can be calculated, depends on the pore structure of the tissue or the material that you are analyzing. So the Darcy's law is generally accepted as the macroscopic equation of motion for Newtonian fluid in porous medium at Lorentz level. So this is another assumption, and that is that the flow, in fact, this assumption is generally satisfied when you look at fluid flow in the tissue. In tissues, that the velocity is very low, and is compared to the blood velocity within blood vessels. Right, so the governing equations for describing flow in porous medium, we have also the mass balance. The mass balance applied to tissues. We also need to consider the source and sink terms. So the source term, the sink term typically, for biological systems, at least the source term usually refers to the flow of blood that comes through the capillaries or permeated through the capillaries into the tissues. The sink term usually describes the lymphatic system because the fluid within the tissues are drained through the lymphatic systems. So the source and sink terms need to be described depends on the system that you are treating or you're interested in. And then this is coupled with the momentum balance, which can be, in the simplest form, can be described using the Darcy's law. So you can solve these equations together to solve for porous medium flows or in simplified homogeneous biological tissues. Right. In some cases, Darcy's law is not satisfied, so we need to make use of the Brinkman equation. So the difference is that, we know in the Darcy's law, it assumes negligible viscous stress within the fluid. So, but in some cases, this is not negligible. It depends on the scale of the problem that we're looking at. So when Darcy's law is not applicable, then the other equation that we can make use of is the Brinkman equation. So this is it all applies to Lorentz and the flows. So the Brinkman equation has got this viscous term in it. And typically, when you decide which one of these equations to apply to your biological tissues of interest, you look at the length scale, and in particular, you look at the permeability. So if the length scale is typically, if the length scale is about 2 orders of magnitude larger than the full scale, then it's safe to use the Darcy's law. Otherwise, you will need to use a Brinkman equation, right? And you will see that when the length scale of interest is much larger, then the Brinkman equation is actually reduced to Darcy's law if you look at the solutions. Mathematically, they will converge to the same solution. Right, so I'll finish off with the oxygen transport in the body for today. Now, if we look at the oxygen transport in the body, this involves multiple processes. So the process starts from up breathing air into the lungs, right? So the breathing of the air through the mouth, and it passes through the large airways and the small airways, and then into the bottom of the lungs, and we have lots of these alveoli. So the alveoli it provides a huge surface area that allows gas exchange to take place. So initially we have convection through respiration, and once it enters into the lungs, there is a diffusion across the lung capillaries. So this process is described over here. So this is the surface of the alveolus, and so this is the air, the fresh air that we breathe in, and it's saturated with oxygen. And then this is the capillary vessels, so that you can see that through the venous system into the lungs that it's low in oxygen, and then through the exchange with the gas in the alveoli, then you can see that the blood is rich in oxygen, saturated with oxygen, coming through the other end. So this is the venous system in the capillaries, and then this will go into the arterial system, into the heart, and ready for the next cycle. So this is where gas exchange in terms of the oxygen and CO2 take place inside the lungs. This is driven by diffusion. So once the oxygen is transported into the blood, it's carried by hemoglobin expressed on the red blood cells. And then the oxygen is transported within the blood through convection, because the blood flows through the blood vessels, and oxygen is carried by hemoglobin in the red blood cells. So we have convective transport. And then when it reaches tissue, at the tissue level, and you have diffusion through the tissues within the cells to mitochondria, and then oxygen is used in aerobic reactions that produce energy. So these aerobic reactions can be described using chemical reaction equations. We have reaction rate. So you can see that it encompasses all the different mass transfer mechanisms. You have convection, diffusion, and reaction. Right. The classical model for oxygen transport in tissues. And so this is always the first model that the students study. This is known as the Croft cylinder model. So the Croft cylinder model, the solution can be derived mathematically, analytically, without need of any computational tools. So the assumption, there are obviously a lot of assumptions. The assumption is that the tissue contains capillaries, and capillaries are evenly spaced with characteristic distances between them. The capillaries supply oxygen to a cylindrical volume of tissue surrounding each capillary. So schematically, it looks like this. So you have, so in the tissues, it's like the tissue has these symmetric array of cylinders. And each of these cylinders is like this. So each cylinder has a capillary vessel in the middle, and that's surrounded by tissues. So that oxygen carried by blood within the capillary vessels is transported through the capillary vessels to the tissues, and then get taken up, consumed by cells within the tissue. So that's the problem that we solve, and then we can make use of the fundamental equations that we learned before to solve these mathematically. So for oxygen transport in tissues, mass balance on steady state, one-dimensional diffusion, and here we assume zero-order reaction. Well, zero-order reaction makes the mathematical equation more easily to solve, right? So if you use the diffusion-convection reaction equation in cylindrical coordinate system, that under this assumption, and that equation is reduced into this form. And then the reaction, assuming that the reaction rate is constant. So I'm sure that you know how to solve these mathematically. And then you can find, so we need to find the concentration of oxygen in the tissue as a function of radial position. So here's the solution. And then So the mathematical solution that include, so this R, this big R, uppercase R is the oxygen consumption rate, and we assume the oxygen consumption rate is constant. And we also have the diffusivity. So this is the diffusion coefficient of oxygen in tissue, so D. And R is the radial position, and the R is over here as well. Now, when we solve these equations, we introduce two constants, A and B. So this A and B need to be determined by applying appropriate boundary conditions. So here, the boundary conditions that, in terms of the mass transfer, the first assumption is that at the capillary wall, because we have an interface between the capillary vessel and the tissue. So at the capillary wall, we assume that oxygen concentration in the tissue is in equilibrium with that in the blood. In other words, you ignore any resistance to oxygen transfer through the capillaries. So again, that's a big assumption, but it makes it easy to solve the equation. And also at the tissue, outside of the tissue, at the edge of the tissue, we have a symmetry assumption, because in the tissue we assume there are symmetric arrangement of those cylinders, and so that there is no mass transfer across the outer boundary. So we have this to satisfy this condition, zero gradient. So with these two assumptions, then mathematically we can find the value for A and B that we introduced from the integrated equations previously, and the final concentration profile in the tissue. So this gives you the concentration profile for oxygen in the tissue, and it can be expressed analytically using this equation. If you wanted to simplify that further by defining some of the parameters over here and normalize the radial positions, and then you end up with this expression. Right. So with that expression, so remember that here we're solving oxygen transfer in the tissue. The tissue has certain thickness. So at the interface with the capillary blood, we have R equals RC. And then at the edge of the tissue, we have R equals RT. So for oxygen to supply, if we wanted to have sufficient oxygen to supply the entire tissue, then we need to make sure that the concentration within the tissue is actually greater than zero, right? Yeah, so we'll be interested in looking at the concentration profile within the tissue. So look at R equals RT. This is at the edge of the tissue. This is the edge of the tissue that is supplied by each capillary vessels. And then so that this R star equals to 1, and then the expression is like this. Now, in order to make sure that the oxygen concentration at the edge of the tissue is greater than 1, then mathematically we can find that this phi has to be less than, satisfy this equation. So you can find the expression of phi from the previous slide. So this actually allows you to analyze whether there is sufficient oxygen supply to the tissue or not. Obviously, if this condition is not satisfied, then it means that the concentration, well, in reality, the concentration cannot drop below 0, but what it means is that there's insufficient oxygen supply to the tissue for the metabolic requirement or metabolic consumption of the tissue, so that the tissue is said to be anoxic or hypoxic. And, well, obviously, if this is in a living system and if it lasts for a period of time, then the cell can die. Right? And, well, obviously this does not happen in normal tissue, but it can happen in extreme conditions, especially when the metabolic rate of oxygen consumption is high, for example, in tumor. So in tumor models, that it is common that there is a region of necrotic regions. Okay, so now there are lots of assumptions. So if you want to study the assumptions and to know the details about all of these, I would refer you to this paper by Goldman in Market Circulation. It has elaborate discussion about each of these assumptions. So first, the major assumption is that the capillaries are identical, they are parallel, evenly spaced, and then each capillary is surrounded by a cylinder tissue, right? So that's the basic assumption. And then assume it's steady state. It does not change as a function of time. Convection and axial diffusion are actually neglected, so we did not consider the change of, or the diffusion transport, the change in concentration in the direction of the vessel. We only considered the diffusion in the R direction. And we assume the oxygen consumption in the tissue is represented by zero-order kinetics with a constant rate and uniform, and this is not true. In reality, that tissue is not uniform, and the oxygen consumption can vary. Now, this is an assumption that we use in the established boundary condition in solving the equation. So this is oxygen concentration in capillary wall equals to the oxygen concentration in capillary blood, right? So that's assumption. And then there are other assumptions. For example, the oxygen hemoglobin dissociation reaction is at equilibrium. Oxygen released in blood occurs uniformly. Again, this does not happen in reality. Other reactions of oxygen can react with other species, and that has been ignored. However, these provide some fundamental tools for us to analyze oxygen transport, oxygen consumptions, transport in tissues. So this is a summary. The cross-cylinder model was actually developed to examine oxygen transport in small vessels, in capillaries, right? So you don't apply these to large vessels. If you're interested in oxygen transport in large vessels, then it's a different matter. So you would have to consider convective transport, and in that case, you probably have to solve three-dimensional equations along with the flow. And well, you can read that even though it has lots of assumption limitations, the cross-cylinder model is an important starting point for understanding oxygen transport in tissues. This model can also be used to study blood tissue transport of substances other than oxygen, for example, glucose. Right, so a significant amount of oxygen consumption actually occurs in arterioles. So these are the vessels in a range of 20 to 100 microns in diameter. And in this range, the blood behaves as, well, in this range, you can still consider blood as a single-phase fluid. And here, that the transport of oxygen from arterioles to the surrounding tissues is actually limited due to the fluid side mass transfer resistance. In other words, the assumption of oxygen concentration being the same at the capillary in the blood and at the capillary wall in the tissue will no longer be valid. So the resistance will become quite important. And there is also significant oxygen uptake by smooth muscle cells, which need to be accounted for. There's a lot of extensive discussion about the various assumptions and justifications in this paper. There are also follow-on paper from the original work and discussing how the importance of each of these assumptions and at what circumstances that those assumptions are no longer valid. So I would encourage you to look at those. I think that's all for today, and we still have time for some discussion. Thank you. Has anybody studied the cross-cylinder model for oxygen transport before? Or is this the first time you're learning it? Okay, good. Have you all done mass transfer in your, no mass transfer, heat transfer? Oh, okay. Well, it's actually quite easy to understand mass transfer because there's a lot of analogies between heat and mass transfer. So you just need to, when you study heat transfer, you're interested in temperature distribution, right? So the equivalent to that in mass transfer is concentration. You have the concentration gradient to drive mass transfer, and the parameter of interest is concentration, just like temperature, right? And then in heat transfer, you have heat conduction. Equivalent in mass transfer is diffusion, molecular diffusion. In heat transfer, you have convective heat transfer, right? And the mass transfer, you have convective mass transfer. So when we teach our undergraduate student heat and mass transfer, we always do that together. So look at the analogy between heat and mass transfer. You also use quite a lot of empirical correlations when you solve for heat transfer problem, right? And you use the, I said earlier, you use the Nusselt number, whereas for mass transfer, you have similar empirical correlations if you don't want to solve it numerically.
Thank you, ma'am. It's a very good insight. When an accidental case like hemorrhage, and there is injury site where fall the level of partial oxygen in the tissue or cell. So there any natural mechanism in the body that recover the level of oxygen at the site of injury.
Oh, interesting question. At the site of the injury. So injury, you mean internal injury?
No, ma'am. Like hemorrhage condition, when very heavy loss of blood, then.
Oh, so loss of blood. You
capillary,
mean
yes.
you mean a cut, like a cut
Yes.
in the surface? I'm not aware of that. I know about the coagulation through platelets when you have a cut, to prevent the loss of blood. But for oxygen at that level, I've not looked into it. Did you say that whether there is recovery mechanism for oxygen? Is that what I hear? What's the question? It's about recovery of oxygen at the cut, the surface, right?
Like there is a hypoxia condition.
Hypoxic condition. Interesting. I don't know. I don't have a strict answer to that, but I've not studied oxygen transport after injury or cut. But it's interesting to think about. Yes, yeah. But I still feel that in terms of the system supply of, so it's thinking about the oxygen saturation in the blood. So it still comes through the mechanism that we described. So the blood that comes to the surface is still rich in oxygen. But then at the injury site, what happens? You can look at, it was also exposed to the atmosphere, right? So yeah, you could look at oxygen transport through the atmosphere to the injured surface, maybe. That's one of the boundary condition.
Any other questions?
Because that's the boundary conditions in Krog model, they seem far too idealistic. So,
Yes, exactly. They're very idealized. So, do you want me to explain the
yeah, like how it
boundary
presents the conditions.
all the boundary conditions? Sorry.
There are just two, right, in the Krog's model.
In the Croft model, there are two boundary
Yeah,
conditions.
so can you just explain how are we presuming those conditions?
Okay. So, how they assumed those
Yeah.
conditions? Well, you come up with the simplest assumption you can make so that mathematically you can solve the problem. So one of those assumptions is that because you have an interface between the blood capillary and the tissue, right? So at the blood capillary and tissue level, you must assume a concentration. So the simplest assumption is that the concentration is the same. So the concentration of oxygen in the blood capillary, in the blood, is the same at the same interface but on the tissue side. because at the interface, you have the blood side, you have the tissue side, right? So you assume there is no, you assume there is no resistance, and so that oxygen is the same on either side. That's the first assumption. But it has been shown later through follow-on research that that assumption is actually a very crude assumption. It's not realistic. So there is actually resistance because if you consider flow in the vessels, in capillary vessels, there is significant resistance at the wall. So you need to consider resistance to mass transfer through the layers. So that continuous oxygen concentration boundary condition at interface is not valid. But it was used at the time to derive the equation. The other assumption is at the outside of the tissue, because we consider each cylinder of tissue has a capillary in the middle to supply oxygen, right? And then because we assume that the tissue consists of a lot of these a lot of these cylindrical tissues supplied by capillaries. So they are next to each other. Everyone is identical. They're all the same. You don't consider the boundary effect. So because in reality, the tissue has a finite length. You don't consider the actual outer boundary of the tissue. You just consider a lot of these identical cylinder of tissues fed by a smaller capillary in the middle of them. So at the edge of the tissue, you assume that it satisfies the symmetry conditions, so there is no, it's like a mirror image of each other, so there is no oxygen transport across the boundary. So everyone is the same. So that's the symmetry condition.
That also isn't realistic.
Well, obviously in reality, that's not the case. Even capillary is not evenly spaced. So here you assume all the tissues and capillary vessels evenly spaced and they're parallel to each other. That's not true. And the other assumption is that the other assumption need to be revisited is the neglect of oxygen transport or consumption in the axial direction, because as blood travels along the vessels, it gets taken up by consumed, right? So there is a concentration gradient in the axial direction as well. It's not just to the radial direction. So that has been ignored. But analytically, you can actually write an equation to look at the oxygen concentration gradient along the capillary vessels in the axial direction, in the x direction. But if you introduce that into the equation, you end up with an equation with a partial differential equation, but you cannot solve analytically, right? You have x and r two directions. Yeah. All right.
When blood flow in small vessels, so there is a plasma skimming layer form. There is no RBC flow. So what is the importance of this plasma skimming layer in clinics?
Sorry, I didn't quite hear the second part of the question. So I heard about the red blood cells, and then what else?
Actually, when blood flow in small vessel, so there is a plasma skimming layer form. At that place, there is no RBC. So, what is the importance of this plasma skimming layer at the blood vessel?
What's the importance of that?
Yeah. So why this is formed, and what is the importance in that skimming?
Okay, so sorry, if I understood your question, it's you're talking about the two-phase fluid model in the blood vessels, right?
Yeah.
Yeah. So no, that's how the flow would behave. So if you have so thinking about the two-phase flow, you have interactions, relative motion between the red blood cells and the plasma, and then when they pass through small vessels, it has been observed that the red blood cells tend to, so there is a very thin cell-free layer, plasma layer, and that does not contain red blood cells. So if you use that observation and then apply to the theoretical equations, then you can solve the flow problem, and then you can look at the thickness of the cell-free layer. It's actually very thin. If you study the paper I cited, the original paper, they've quantified the thickness of the cell-free layer, plasma layer.
Okay, thank you.